Okay, let's dive right into this. Have you ever wrapped a non-magnetic shield around a wire thinking, that you've just created this bulletproof barrier against magnetic interference? It's a super common intuition, right? But in the world of electromagnetic compatibility, or EMC, relying on that intuition can literally lead to failed compliance tests. Today, we're going to absolutely shatter the myth that a simple, ungrounded shield magically stops magnetic fields at low frequencies. Mastering the true physics of magnetic coupling won't just expand your theoretical knowledge. It's absolutely crucial, and it's going to directly save your real-world designs from those critical, hard-to-diagnose failures.
Here's our roadmap for today. First, the magnetic shielding illusion. 2, inside the coaxial cable. 3, the math of shielding. 4, a frequency response walkthrough. 5, the common impedance trap. And finally, our key takeaways. Let's get into it.
Section 1. The magnetic shielding illusion. Why low-frequency shielding fails.
So why do non-magnetic shields seemingly fail completely to protect our conductors against magnetic fields at low frequencies? Well, I want you to visualize an ungrounded, non-magnetic shield wrapped around a conductor. When a low-frequency magnetic field approaches this shield, it acts exactly like a chain-link fence trying to stop the wind. The magnetic flux simply passes right through the shield as if it wasn't even there. It doesn't alter the geometry, and it doesn't change the magnetic properties of the medium. Because of that, direct induction from an outside noise source goes straight into your inner conductor. If the shield isn't grounded properly to actually allow a current to flow, it is fundamentally invisible to a low-frequency magnetic field. No way around it.
Moving on to Section 2. Inside the coaxial cable. Zooming into the atomic structure.
To really understand how this happens, we have to look past the surface and dive straight inside the material. Now, in a standard tubular conductor, if current flows uniformly around its circumference, it produces a magnetic field entirely external to the tube, meaning there is zero magnetic field inside the cavity. But when we place a center conductor inside that tube to form a coaxial cable, all the magnetic flux produced by the current running through the shield entirely encircles the center conductor. Think of the shield current as a massive industrial fan. When the current flows, this fan blows exact, counteracting air to perfectly cancel out the incoming wind of the external magnetic field. Because all the shield's flux encircles the inner conductor, the mutual inductance between the shield and the center conductor, which we call M, is exactly equal to the self-inductance of the shield itself, L subscript S.
Section 3. The math of shielding. Deriving the rules.
So how does this physical reality translate into mathematical proof? Well, this equivalent circuit brilliantly illustrates our setup. We've got a center conductor and a shield. V subscript S represents the noise voltage induced into the shield from some external source. L subscript S is the self-inductance of the shield, R subscript S is the shield's resistance, and M is that mutual inductance between the shield and the inner conductor we just talked about. Finally, V subscript N is the resulting noise voltage induced into the inner, center conductor. Our ultimate goal here is to figure out exactly what V subscript N is.
Okay, so the absolutely crucial point here is how these variables interact algebraically. We're going to break this down step by step. Step 1, the noise voltage induced into the center conductor, V subscript N, equals J omega times the mutual inductance M times the shield current, I subscript S. Now step 2, what exactly is the shield current? Using Ohm's law for AC circuits, I subscript S equals the shield voltage V subscript S divided by the shield's impedance, which is the quantity J omega L subscript S plus R subscript S. Okay, ready for step 3? We substitute our shield current equation into our noise voltage equation. And honestly, here is where the magic happens. Remember from our geometric fan analogy that mutual inductance M equals the shield's self-inductance L subscript S? Well, when we substitute L subscript S for M, the math simplifies beautifully. We arrive at equation 2-25, V subscript N equals V subscript S multiplied by the fraction J omega divided by the quantity J omega plus the ratio of R subscript S over L subscript S.
Section 4. Frequency response walkthrough. Applying the math.
Let's take that rigorous mathematical framework we just built and actually apply it to a practical frequency graph. If we plot the noise voltage in the center conductor against the logarithm of angular frequency, we see that at direct current, or very low frequencies, the noise voltage is just 0. But as the frequency increases, it climbs steadily until it hits a very specific mathematical threshold, 5 times the ratio of R subscript S over L subscript S. Once the frequency exceeds this exact point, the curve flattens out, and the noise voltage, V subscript N, practically equals the shield voltage, V subscript S. The high-frequency noise couples almost perfectly. It's a real eye-opener.
This transition point is so incredibly critical that engineers gave it a special name, the shield's cutoff frequency. It's denoted as omega subscript C, which equals R subscript S divided by L subscript S. Or, if we're talking in terms of hertz, F subscript C equals R subscript S divided by 2 pi times L subscript S. This standard dictates your cable's high-frequency noise immunity. If your operating frequency is much higher than the shield cutoff frequency, the shield current approaches the center conductor current. It acts as a common mode choke and actually provides excellent magnetic shielding. But below this cutoff, your shielding effectiveness rapidly deteriorates.
Section 5. The common impedance trap. The hidden gotcha. Now that we have the math firmly under our belts, we really need to pivot to a major pitfall. It's a hidden trap that frequently ruins circuit performance, even when engineers think they've shielded everything perfectly. So, I want to ask you, what do you think happens when the shield is functioning as your barrier against external noise, but is also acting as your primary signal return path?
If you do that, you have just walked right into the common impedance trap. Let me explain. When you ground a coaxial table shield at both ends to protect against low-frequency magnetic fields, an induced noise current flows through that shield. But if you are using that exact same shield as your signal return conductor, you have a massive problem on your hands. Let's sum the voltages around the input loop. The input noise voltage equals negative j omega m times shield current, plus j omega L subscript S times shield current, plus R subscript S times shield current. Now, because we've already proven that mutual inductance M equals shield inductance L subscript S, those two inductive voltage terms completely cancel each other out. So what are you left with? V subscript IN equals R subscript S times I subscript S. You are literally left with a purely resistive noise voltage injected straight into your signal path. It's a total nightmare for signal integrity.
Luckily, the solution to this dual-function nightmare is beautifully simple. You just decouple the responsibilities. Use a 3-conductor cable, like a shielded twisted pair. The 2 inner twisted wires handle your delicate signal and its return, while the outer shield has only one job, carrying the noise current safely to ground. By doing this, you completely eliminate the common impedance coupling trap. Problem solved!
Section 6. Key takeaways and outro. The rules of magnetic coupling.
We have covered a lot of ground today, all the way from theoretical physics to some really rigorous mathematical derivations. So here are your 3 rapid-fire takeaways to ensure your next design easily passes EMC testing. Number 1. Ungrounded shields act like chain-link fences in the wind. They absolutely fail to block low-frequency magnetic fields. Number 2. To get true magnetic shielding, you need shield current to flow and cancel the flux. This is a reality governed by the rule that mutual inductance equals the shield's self-inductance. And number 3. Beware the common impedance trap. Never, ever force your shield to carry both noise current and signal return, or you will directly inject resistive noise voltage right into your circuit.
So I want you to take a hard look at your current schematics. Could your signal return path be secretly compromising your entire EMC compliance strategy? Understanding these core rules is exactly what separates a guessing game from true precision engineering. If you found this explainer valuable, hit subscribe for more EMC and automotive communication protocol survival guides. Keep learning, keep building, and I will see you in the next explainer.